Okay, we're going to wrap up section 5.3 today. We're going to go over using this multiplication rule for independent events. We did do the general multiplication rule last lesson, but now what happens when they're independent? Okay, and then another spin-off example using that. All right, so right here, 5.3.4, pause and find this part of your notes. Okay, so here's the general multiplication rule we used before. But sometimes, if they're independent, the given condition doesn't affect anything. So when does it affect it? So just real quick, a real basic example. Let's just say we're talking about drawing two hearts from a deck. So probability of getting the first heart is 13 out of 52. But the second heart, given the first one was a heart, is now going to change, right? Down to 12 out of 52. Okay, but if I made this an independent setting, we wouldn't have to worry about that. It'd be the same. So if I draw a card, okay, it's 1/4 or 13 out of 52, I put the card back in, reshuffle, now the probability is the same. All right, so if they're independent, you just keep multiplying by the same probability, or I guess it could be different if they're different events, like drawing a heart and rolling a 6 from a die. That's once again two independent events. If the outcome of the first event doesn't affect the second, it's going to be independent. Okay, so simply put, just the two probabilities multiply together. Okay. All right, so let's take a look at example 20. The Challenger disaster. Take a moment to read that, or pause. I'm not going to sit here and wait, so pause and read it. Okay, so early on, once you start reading this, like, all right, 0.977, that's even kind of low for sending people to space. You want that to be as close to 1 as possible. So even closer would be a good thing. All right, but what's shocking is when you really do the math, there's 6 of these, not just 1. 6 of these O-ring joints are independent of each other. So find the probability that it launches safely. So the probability of a safe takeoff would mean all 6. So it's probability of event A times event B times event C and so on. All the same. So 0.977 to the 6th power ends up being the probability. Okay, and that's not good, right? Only 87% chance that all of these succeed together at the same time. Okay, so there's the answer to that one. All right, so once you're done writing that down, let's go ahead and take a look at the next example. Okay, not the easiest example to introduce this concept. If you didn't finish reading this yet, pause and read the setting. All right, but the probability of at least 1 and none are opposites. And you're going to see that unfold here. All right, so the false positives. Remember, the false positives mean they got a positive test, but they actually had no HIV. Okay, this is just an instructional thing here to help you. You don't have to write this part down. All right, but they said no antibodies are present, and the probability of getting a positive test for those people was 0.004. Okay. So that's kind of the probability numbers we're using too. This is another part I write down. Let you write down probability of getting a positive under this scenario with no HIV antibodies is 0.004. So the probability of a negative is 0.996. Okay. All right. So another thing, I don't think you need to write this part down, but I'll tell you what you need to write down. This is just kind of an instructional tool to show you. This is really what's going on here, right? If I have X, if I let X equal the number of people that actually have a positive test, it could range anywhere from 0 to 200. Obviously, 200 is going to be very unlikely, but those are the outcomes. Okay, and each of these have their own individual probabilities. We could have 0 people, we could have 1 person, we could have 2, and all of these make up the probability distribution. Okay, so they're asking for, though, what is the chance that at least 1 false positive will occur? Remember, all the positives here are going to be false positives because they don't have any. So at least one would be the sum of all of these. We need this, plus this, because these are at least one, correct? Right? 3 is at least one, and so on. That's a lot. Like we we don't even know how to find these yet. We will in chapter 6, but even when we do get to chapter 6, we're not going to have to do them all. There'll be shortcuts. Okay. So here's the shortcut to this one, right? Since I need at least one, all of these, can we figure out this one? Sure we can. So once I figure out this, I just got to realize that's the only thing I'm missing from this entire distribution. So I do 1 minus that. Here's an important thing to write down. Okay. Here's what we're going to use. The probability of at least one will be always equal to 1 minus the probability of none. Okay. All right. So it's going to make our job easier. We don't have this part yet, so I wouldn't write that part down yet. All right. So that's what we need to go find. If we can go find the probability of none, we'll be good to go. All right. So for x equals 0, this is the part you might want to write down now. If none are positive, that means they were all negative. Okay, if none of them had the positive tests, right, that means all of these are negative. So we want the probability of 200 negatives. So it's 0.996 raised to the 200 power. Okay. If it was flipped and we're looking for all are positive, it would be 0.004, but we're not talking about that. That would be this number over here. Okay. If 0 are positive, that means all of them were negative. Okay. So it's 0.4486. That's basically the number that we should have there in that distribution. Okay. So now we can finish it. Probability of at least one positive is 1 minus that box. 0.5514. Okay, the check your understanding actually doesn't address this one. I'll give you a couple in the OTI that do. Also with a worksheet in today's assignment will be bookwork and worksheet. I'll let you guys pause for a moment, try this check your understanding, and then I'll give you some feedback on that, and then do the last page. Okay, here you go. The probability of being lost is 0.05, and the probability of it returning safely is 0.95. So if all 20 are going to come out and be safe, that's the result. We're going to take 0.95, raise it to the 20th power, or multiply it by itself 20 times. 0.358. Okay, so there's about 36% chance that all 20 return safe. Okay, I'm going to pause the video as you turn the page and read the first half of the next page to think about it, and then we'll discuss it in just a moment. Pause and read. Okay, so I actually did the independence test over here to help you understand this. Obviously, I hopefully understand that these are mutually exclusive, right? Can't be male and pregnant. There's no overlap to this. There aren't males that are pregnant, right? It's one or the other. So they are mutually exclusive. And they don't pass the independence test, right? So for example, that's the probability of somebody being male, roughly 50%. What's the probability, given they're pregnant, that they're male? 0. They're not equal. Or even if you flipped around these conditions, it's not going to work. Probability of being pregnant, I don't know. I just kind of made this up. Maybe 1 or 2% of the population is pregnant right now. But what's the probability, given that they're male, that they're pregnant? 0. It doesn't work. It doesn't pass the independence test. Okay. I don't know if you read all of this or not. If you didn't read these other 2 scenarios, pause and read it. I'm going to keep going now. I just kind of gave you another follow-up example to this. These are also mutually exclusive, like these are. Either it's a red or it's a club. Can't happen at the same time. Okay? Because clubs are black. All right. So can't happen at the same time. So are they independent? So I went through the independence test. Didn't work again. So they're not independent. So there's another follow-up here. If you want to write down in summary, if events, well, hold on, I'm getting ahead of myself. So does that mean if they're not mutually exclusive, does that mean they are going to be independent? Not necessarily. Okay. So I went through and explained that here. Basically, if they are not mutually exclusive, then you're going to actually have to use the test for independence to see if they are or not. So this could be either or. This is the only one you can really count on. If they are mutually exclusive, then they are not independent every time because they are dependent, right? Not independent means they are dependent. Okay. All right. So I'll pause, or you pause that if you want to write down the summary of rules. And that's it for 5.3. Have a good day.